And hello, welcome everyone. Welcome back to this video. So today we want to talk about solutions to the von Karman equation. Hopefully in a few videos time, I'm going to compare it to the similarity solution. Just a caveat for similarity solution, I'm not deriving how to solve that. You can either use a Runge-Kutta-Foer method or a what do you call that? Yeah, Frobenius method, which is to substitute a series solution, like I talked about a few videos back. Yeah, that's how you get the Blasius solution. It's an exact solution for boundary layers. Von Karman is more approximate, but of course von Karman is slightly somewhat easier to solve. Okay, and here is the solution procedure. Okay, for von Karman. Okay. For von Karman's solution procedure, it was first developed by this guy, I think, Pohlhausen solution. So Pohlhausen's solution. Pohlhausen. I have no idea how to pronounce his name right, but I'll just call him Pohlhausen for now. If you know how to pronounce it properly, leave it in the comments or something. Yeah. So what is his solution? He assumes that, very simply, the velocity follows a cubic profile. So, for example, velocity equals to a, which is some constant, plus by squared, by plus cy squared plus dy cubed. Of course, you can put other forms of other functions as well. But I mean, this is pretty intuitive. Okay, you can always assume a series solution and you truncate at the y cubed term, y to the fourth term. So that's what he assumes. Okay, assuming this is true, okay, how then do we solve it? Okay, we basically substitute this all the way back in here and find the appropriate boundary conditions. So let's just do that. Okay, so we don't just substitute this solution form in first. We also need to consider the boundary conditions. Okay, so where do we get A, B, C, and D? We get it from the boundary conditions. So what are some of the boundary conditions? First, we have no slip. Okay, what's a no slip? U, okay, the x velocity equals 0 at y equals 0. Okay, so let's just write that down. U equals 0 at y equals 0. Pretty straightforward, right? Okay, U equals 0 at y equals 0. What does that mean? This implies A equals 0. Okay, A equals to 0. Okay, I mean, so that is one. That makes things a little bit easier. Now what's the next thing? Okay, what's the next thing? Okay, next thing, okay, is as y goes to a very big value, okay, y goes to a very big value, u becomes u infinity. Okay, y right arrow infinity, u equals to u infinity. All right. Now there is a good sense to this. There's a very intuitive sense to this. Unfortunately, as y goes to infinity, all right, as y goes to infinity, u will of course go to infinity in this kind of form. Alright, if y goes to infinity, then u is going to go to infinity. So that's not going to really work very well. Okay, so what can we do? We can alter this slightly because, yeah, let's instead of going to u infinity, let's go to this boundary layer thickness. Okay, so as y approaches this momentum boundary layer, u goes to u infinity. Okay, that's close enough, right? So there's an approximation we make here. Okay, when y equals to delta p, the momentum boundary layer thickness, u as u infinity. Of course, you can make it such that at delta p, u equals 0.99 u infinity. So you can absolutely substitute that in as well. It will work well. It will just, of course, change your B, C, and D numbers a little bit more. But it's not that not huge, right? I mean, you can of course put 0.99 u infinity for the proper boundary layer thickness. It will just pretty much do the same. Okay, so approximation is when you don't put that 0.99 in. Exact is like so. If you want to put it exactly, okay, exact. So I leave it to you. You can put either of these in. This one is slightly more exact sort of boundary condition based on our definition of the momentum boundary layer thickness. You can substitute that as in as well. Though in your standard von Karman derivations, that's not being used. But and of course, if you substitute this in, your numbers will change slightly. And you can try it yourself. But for the time being, I mean, most people in their standard derivations, they will use this instead. Okay, they will use this instead. Yeah, though for simplicity's sake, I mean, these make nicer round numbers, to be honest. Okay, when y equals delta p, u equals u in infinity, that makes a very, very nice round number for what we're doing. Okay, and that's how it was originally done. Okay, so we'll just take this velocity profile, no problem. Now we'll just take this velocity profile. What else can we say? Okay, next approximation we want to make. Okay, next approximation we want to make. Okay, inviscid flow near delta p. Wow. Yeah, my computer was making a little bit of noise. The fans were getting a bit noisy for some reason. Anyway, let's assume inviscid flow near delta p, and shear stress is 0 there. So near the boundary layer, remember we were talking about Bernoulli's equation, right? Okay, so towards the edge of the boundary layer, closer to the bulk fluid, that's where we have the assumption of inviscid flow, where the viscosity terms are kind of neglected. So that's what we are going to do here as well. Okay, this is again another approximation. Partial u partial y equals 0. At how do we put this? Okay, let's see. Yeah, at y equals to delta p. Okay, never mind. Yeah, we'll just continue. Okay, so basically we have 3 boundary conditions. We need one more, but let's first develop some equations. So from this second boundary condition, what can we say? We can substitute these values of delta p, u infinity into this equation here. So I'll use this begin equation u infinity that's u infinity equals to b delta p plus c delta p squared plus d delta p cubed. This is just the velocity boundary condition. Okay. There. That didn't do too well. Well, okay, this is what it should look like. Okay, and of course, if you have your 0.99 U infinity substituted in here, you can imagine the solutions will look a bit different. 0.99 will be on the left hand side. Okay, so this inviscid flow assumption, what's this inviscid flow assumption like? Okay, this inviscid flow assumption, you'll have to then differentiate this everything here. So let's differentiate. Okay, fraction partial u partial y equals to, okay, b plus 2cy plus 3dy squared. Okay, so now we will need to put in another we'll need to put in another what do you call that, boundary condition. So we'll just let's see. Okay, we'll substitute 0 here. 0 equals to b plus 2cy, y equals delta here, and then you have delta p squared, and you will have an equation looking something like this. You have an equation looking something like this. Alright, so that's your next equation. Now for the last BC. Okay, so let me write this down first. This is exactly what is said in the textbook. So partial square u partial y square equals to 0 at y equals to 0. How are we supposed to interpret this? Okay, how are we supposed to interpret this term right here? Okay, we know du dy has something to do with shear stress, right? Shear stress. Okay, so what this is saying is that, in other words, some way to think of it, tau x, okay, partial tau x partial y equals to 0 at the wall. So this is the physical like interpretation of it. Okay, partial tau x partial y equals to 0 near the wall. Okay, and this is also sort of an approximation, I guess. Yeah, but this is basically saying that let's see. Let's use this as a visual. Okay, there's tau x going here, and then this is your boundary layer, right? Okay, so the near the wall, tau x near the wall, at the wall, and tau x slightly away from the wall is pretty much the same. After that, you can sort of change it a bit. So I mean, it's not too hard to imagine this, that the shear stress at the wall is very close enough, pretty much, to the shear stress just a little bit away from the wall. Okay, and the other way of thinking about this is that the other way of thinking about this is that if tau is constant, then del u del y is constant. Okay, del u del y is constant. That means near the wall, the velocity profile does look like a sliding flat plate flow. Okay, so it's a linear velocity profile near the wall. Okay, that is essentially what this thing is assuming. After that, it will change as and how it likes. Okay, so it assumes this sort of linear velocity profile near the wall. Is it? Hope that is clear. I mean, it's not the most obvious assumption to make, but that is what is being made. Okay, and if you were to think about it, okay, maybe a easy way to visualize is this. If you think about, let's say, a boundary layer like this, it's a BL. Okay, and the velocity here will be more or less constant, u infinity. Okay, this is a flat plate, of course. We are solving for flat plate flow, and then of course you have this sort of flow profile. So have this sort of flow profile, right? We don't know how this thing will curve just yet, but it's not unreasonable to say that maybe here at the start the velocity profile is linear. So it's constant near the wall, and this velocity profile starts off as linear, and then maybe it branches out a little bit more to the outside. I mean, yeah. So that's it's not too far of a stretch. Okay, if you know what I mean. Not too far of a stretch to say that the velocity profile is more or less linear near the wall. Okay, so that's sort of an approximation, of course. It's not 100% accurate, but it's not. But if you think about it, it's not too far a stretch to make. Okay, and it will make your life a lot easier as well. All right. So how does this get translated into a boundary condition? Yeah. So what happens is that when you want to do del 2u del y square, okay, del 2u del y square. So what do you do? The b will disappear. B will disappear, and then you'll have 2c. Okay, 0. Okay, or you just put 2c plus 6dy, right? 2c plus 6dy. All right, so it's 2c and 6dy, and all of this will be equals to 0 at y equals to 0. So this will be equal to 0 at y equals to 0. So let's substitute y equals to 0 and y equals to 0. Then this whole term here will disappear, and this second derivative will also disappear. And then what we get? 2c equals to 0, or c equals to 0. Okay, so that's what we will get. Okay, so c equals to 0. And what other equation do we have? We have this equation here. Okay, so two equations left. All right, which is this one. Okay, this one. Where's that delta p equation? Yeah, this one. And of course, depending which one you want to solve, we have this. All right, so two equations, two unknowns. That's a pretty standard way to solve. C equals to 0, so let's get rid of the c terms. Yeah. Okay. So what do we get here? Okay. Okay, we can of course solve this b equals to minus 3 delta p squared. b equals to minus 3 delta p squared. Okay, b equals to minus 3 delta p squared, and okay, b equals to minus 3 delta p squared. So we have minus 3 delta p cube, minus 3 delta p cube plus d delta p cube. Okay, so looks like d is pretty straightforward to get. Alright, so we divide both sides by delta p cube. Okay, I think I forgot something. There was supposed to be a d there. Let's put in the d. I forgot the d totally. So 3d minus okay, yeah, you just add these two terms together, it becomes minus 2. And we can finally get an expression for d, which is a negative number. Okay, d equals to what? Minus fraction u infinity divide by minus 2 delta p cube. Okay, so this is in terms of the boundary layer thickness. Okay, let me get rid of the minus sign at the bottom. Of course, you want to put 0.99 u infinity, you just replace u infinity here by 0.99 u infinity. Yeah, so that's depending how you want to do your boundary layer comparison. Alright, I think I'm running over time, so I'll stop for now. I'll continue more in the next video. Okay, bye.